Hello everyone. My name is Jerry and 林真者. Okay. Then we are going to present this paper, high durable bio-in-space self-cleaning solid liquid contact triboelectric nanogenerator for water wave energy harvesting. And this paper is from the journal Nanoenergy. And this is outline. So introduction. Let me first introduce the background of this research. Ocean wave energy is very rich, but it's hard to use because in the ocean, materials break down easily, and ion in water can weaken the electricity we try to collect. And triboelectric nanogenerator or TNGS are small devices that can turn motion into electricity, and they are good for floating energy from low speed movement like ocean waves. But solid liquid TNGs have some problems. They often lose power because of ion buildup and dirty or battery that stick to the surface. And this is called biofouling. And to solve this, the study design a new surface. It is inspired by the lotus leaf, and which is famous for staying clean. And this surface uses tiny micro and nanostructure and a special charged FEP material. And this smart design helps the device stay clean, hold more electric charge, and work better in the ocean for a long time. Next page. And this device is a solid liquid triboelectric nanogenerator or TNGs, designed to work in water. So it has a visible layer structure, including a self-cleaning top layer and electrode layer with resistive circuit and a soft PET base layer. And the special part is the top layer, and it's made of FEP film, which is known for being water resistant. And to improve performance, the surface was made into a micro and nano structure, like a lotus leaf. And next page. And now let me explain how the spatial surface of the BSC TNG was made. In Figure 8, the team used a two-stage process to make the micro and nano structure. And step 1 is to make a silicon mold. And they use photolithography and ICP etching to create a pattern on the silicon wafers. And this pattern has a micron-sized holes with small nano bumps inside. And you can see the image B. And step 2 is to transfer the pattern to FEP film. And they press the FEP film onto the silicon mold using high temperature and high pressure. And this creates a pattern on the surface. But the surface is not thorough enough, so they use another ICP etching state to 8 nanowire on top. This makes the final BSC surface with both micropillar and nanowire. And this structure can trap air and make the surface super hydrophobic. Image C and D show the SEM picture of the FEP surface after fabrication. And you can clearly see the micro nano pattern, and the contact angle is 168 degrees, and which means water roll off very easily. And this spatial structure helps the device to stay clean, hold charge, and work better in water environments. And next page. In Figure E, and we can see the AFN image. This shows the 3D surface shape, and the image tells us that the surface has micropillar and nanowire, and this makes the surface very root, and which is good because root surface hold more electric charge. And in Figure F, we see EFN phase shift images that show us how electric charge are spread on the surface, and the color difference in the images show how strong the surface charge are. And this means that the surface can store charge well. When water touches the surface, some charge is lost. But thanks to the raw nanostructure, many charges stay trapped in the deep part. Next page. And as shown in figure 3A1, the BSC surface is first charged using corona discharge, which adds a large number of negative charge onto the surface. Then when the surface comes into contact with water, as in figure 3A2, a lot of these charges are released through tip discharge, especially from the top of the nanostructures. However, because there are many air pockets trapped inside the root structure, some of the negative charge are still safely stored deep inside the nanowire. So these deeper areas are not fully touched by water, so they can keep the charge stable for a long time. We see the electric potential map created by console simulation show that the bottom part of the nanostructure holds more electric potential, so which means stronger ability to generate power. Next page. And in figure 3D, we see four stages that happen as water wave pass by. Stage 1, the surface is dry. The FEP film hold negative charge and the electron are at the same level, so no current flows. And stage 2, water start to move in from the left. It's touch electron A and positive ions from the water attack negative charge from A. So now current flows through the external circuit. And stage 3, water move further and touch electrode B, and the charge keep flowing now between B and C, creating a second current peak. And stage 4, all three electrodes are underwater, charge become balanced again, and current stop. After that, when the wave move away, the process happen in reverse, and we get another round of current. And in figure A and B, we see that the micro nano surface traps air pockets, and which help water stay on top without sticking, like a lotus leaf effect. And figure C compares surface with the and without negative charge. Both have high contact angle, around 164 to 168 degrees, showing they are super hydrophobic. But with charge, this slight angle is the bit larger. In figure D and E, we test how much the water sticks to the surface. Surface without charge showing lower active force. And with negative charge, the surface still resists water, but slightly more force is in it. And this shows the surface is still very self-cleaning, even when holding electric charge.
This slide shows how the BSC-TENG can clean itself using water droplet and waves. In figure F, we dropped water onto a surface covered with carbon powder. You can see that when the water bounces or rolls, it picks up the carbon and carries it away. By stage V, most of power is removed, showing that just a few water drops are enough to clean the surface. In figure G, we used wave movement to clean the surface. As the wave goes across the dirty surface, it washes away the particles step by step. After several wave cycles, the surface becomes completely clean without any chemical cleaning. To test the up to performance of the BSCTENG when young water touches the surface. In Figure A, we see the experimental step. The BSC filling is placed in water, and the water level moves down at about 3.8 hertz. Figure B shows how the device works. In Figure C, the current output shows stable around 4 microampere. Figure B shows the transfer charge is about 60 60 nanocoulomb per cycle. This slide compares the output of BSC TNG with different surface types. In Fig E, we see that BSC gives the highest output around 6 nanocoulomb, while flat surface give the lowest. This is because BSC has the best water repellency with a contact angle of 168 degree. Fig F shows how salt affect the output as salt concentration increase. Most surface lost performance, but BSC still keeps high output, showing strong resistance to ion interference. In Fig G, we test BSC in sea water over time. Even after 13 minutes, BSC still keep high output, while other surface drop a lot. The last Fig H shows performance in different humidity. BSC works well even at high humidity, up to 99%, which is important for ocean application. This type proof it can be used in real ocean environment. The BSC TNG floats on the ocean, collect wave energy and powered wireless sensors to send environmental data. Fig B shows the output current and the transfer charge when harvesting energy from salt water. In Fig C, they measure current and voltage with different resistance. Fig D shows the power output. The best power happened was when resistance is about 10 million ohm with around 3 milliwatt. Finally, in Fig E, we charge different capacitor. Can see the 47 microfarad capacitor reaches over 10 volt in just 4 minutes. This part shows that the BSC TNG can really power a wireless sensor. In Fig F, we see the BSC TNG is connected to a sensor module, and it sends out real-time data like temperature and humidity. Fig G shows that the system can charge 680 microfarad capacitor in about 15 minutes, and then send out a wireless signal. Fig H is a durability test. Even after 35 days, the BSC TNG still keeps a stable current, which means it is very reliable in long-term use. In Fig I, we look at the surface after 35 days. BSC still keeps its clean structure, while flat and the narrow wire surface are covered with dirt and biofilm. Conclusion: bio-inspired micro nano FEP surface was created to achieve super hydrophobic and the surface clean ability. The BSC TNG shows strong performance, voltage around 1,380 volt, current around 24.8 microampere, power density around 3 milliwatt. The system can power wireless sensors showing promise for blue energy harvesting.
I just had to let you know you're. She had me, baby, she